Hello everyone, and welcome to this series of videos on physics of fluoroscopy for the pain medicine exams FFPMRCA. Hopefully by the end of this series you will have all of the knowledge you need to answer any questions that can pop up related to this topic, and it is a fairly important topic. It's something that we use in our day-to-day interventional pain practice. It's something that the examiners are going to expect you to be fairly familiar and confident about. Now, if you haven't visited our website, painrevision.com, please give it a go. I'm building a resource that should cover all of the knowledge base that you require for the pain medicine exams and beyond in order to just make you a better pain medicine physicians and cover various aspects of pain medicine. So let's dig right in. Fluoroscopy utilizes X-rays. X-rays are a form of ionizing radiation, and so one of the first questions you might get asked is, what is ionizing radiation? And simply put, ionizing radiation is a form of energy. What makes it different from any other form of energy? The fact that the energy is extremely high, that it can displace electrons off their atoms, which means it can create ions, and that's why it's called ionizing. And this is an important concept because that is directly related to why it can cause damage, and we'll come to that in the next video of the series. But for now, it's basically a form of energy. It can travel either as waves, electromagnetic waves, or as particles, and it can displace electrons off their atoms, which is the concept of ionization. And depending on the way this energy is traveling, we call it different things. So if it is traveling as waves or rays, we call it X-rays, gamma rays. If it is traveling as particles, we call it alpha particles, beta particles, and neutrons. And each of these forms have a different heaviness. So the heavier the energy is, the less penetrative power it has, so the easier it is to be stopped by material. And as an example, we have the alpha particles right here. So the alpha particles are the heaviest, and so they don't have quite a lot of penetration at all, and they will be stopped by paper. That doesn't relate to their biological effect or damage. So although they're the ones with the least penetration, they are the ones with the most damage. So there is no link really between the amount of penetration and the biological damage caused. The common examples that we have are X-rays and gamma rays, and both of these have a similar penetrative power and also have a similar biological effect. So they'll both be stopped by lead, which explains why, from the safety point of view, we wear lead gowns and lead thyroid shields and so on. Before I talk about the physics of X-ray and its generation, I'll touch briefly on the anatomy of the C-arm and what fluoroscopy is. I will make another video in the theatre suite which will go through the C-arm we have, explain its components, explain the language that you should use when trying to move the C-arm in various directions. And this is very, very important. As a pain medicine consultant, you need to be clear on the language you use. It needs to be the correct terminology, and you need to be aware of what the C-arm is capable of doing and what could be modified so that you can produce the best image. For now, we'll just use the picture we've got on the screen here. At the bottom, I've got the X-ray tube. This is made from tungsten and is what produces the X-rays. I will talk about why tungsten is important in the next slide. And before the X-rays reach the patient, you have got a couple of collimators here. So a circular collimator and a square collimator. They call them the iris and the linear collimator. A collimator basically is a way of filtering the rays coming out so that they're all parallel, traveling in a parallel direction. So if you think of it, it's a way of removing excess radiation and removing the background picture that you don't need. So basically, it's a safety mechanism. It's a way of reducing the patient's exposure and your exposure. And you will see radiographers use this on their own accord. So they will, if you think of it, if you're taking pictures of the lumbosacral spine, you're targeting the medial branch blocks, so you've got the vertebrae and you've got the pelvis, you will find that the radiographers might use the linear collimator so that you've only got an image of the bony vertebra and not of the background around it. And you could ask your radiographer to use the circular collimator if you wish, or the linear, depending on what you're imaging. After that, we've got the patient right here. It is important the direction where the X-ray tube is. So normally this is below the patient, not above. This is again a safety feature. We'll talk about it in the next videos. And then on the other side, you have got the image intensifier. This is where the X-rays will be received, detected, and then transduced to the display monitor where you can see your image. You've then obviously got the various motions of the C-arm and the various locks. So you can move the C-arm in various directions, and I'm not going to touch on that in this video. I will probably be better explained in the video in the theatre suite where I'll go through all of the motions. And so if you get asked, what is fluoroscopy? Fluoroscopy is a technique for continuous repulsed X-ray images to produce real-time imaging of internal structures. Again, brief and succinct definition. And now is the scary bit. I find that a lot of people are scared by physics, but actually I think if you really understand how it works, it makes life so much easier for you. You don't actually need to remember it because you understand it, and so you can just basically say it out if asked about it in the exam. And this image is actually a real image of the X-ray source that will have tungsten inside it. I hope you can see my arrow here. We've got, just like anything, we've got the cathode on one side, the anode on another side. You've got an electrical circuit that will be connecting the cathode and the anode, and then the X-rays will be coming from between the cathode and the anode. And this is tungsten. So the material you see here is tungsten. So this is just a diagrammatic representation, which probably makes the explanation a little bit easier. So again, the same picture, you've got the anode on one side, this is tungsten, you've got the cathode on another side, this is again tungsten, you've got an electrical source that connects both the anode and the cathode. And so as electricity goes through this way into the cathode, it heats this filament, and the heating of the filament releases electrons. And so electrons basically are negative, they are attracted to the tungsten on the other side, and essentially travel through this distance to the anode. Now, as they travel through to the anode, because they're attracted to it, they're basically going at a high speed towards the nucleus of the tungsten atoms. And as they approach the nucleus, what happens? So imagine the circle here I've got here is the nucleus of the tungsten, and you've got the speeding electrons going around by the power of attraction. As they're speeding around, kind of like an orbit, how a spaceship will be attracted to the to the gravity of a planet, and then will basically decelerate and orbit around it. The same thing will happen. So the electrons with high speed, as they're attracted, as they get closer to the nucleus, they will start decelerating and turning around the atoms of the tungsten. And because they're decelerating, they're losing kinetic energy. And because they're losing kinetic energy, that energy has to go somewhere, and so that energy is released as a photon, which is the X-rays that you can see here. So basically, this is the main way of producing X-rays. It is called Bremsstrahlung. This is a German word. I'm sorry if I've completely butchered the language, but it literally means braking radiation. Braking as in the brakes of a car. And so you understand the concept, because the electrons, as they're going around to the tungsten at a high speed, they brake and they slow down, and that slowing down is what causes the release of energy. Why do we use tungsten? For a couple of reasons. Basically, it has a very high atomic number. So the material itself will have a large number of atoms, and that large number of atoms means that it's more efficient at producing X-rays, but it also has a very, very, very high melting point. So for those two reasons. Now, when you get asked how X-ray is produced, it is through two mechanisms. The main mechanism is this one, Bremsstrahlung, and this probably produces more than 90%, I think if I recall correctly, 98% of all X-rays. And these will be photons of different energy, because depending on where the electrons go and where the location of the atom is and how they decelerate, the amount of energy produced will be fairly different. And so this will produce a number of X-rays of varying energy. The second way of producing X-rays is through a characteristic radiation, which produces around 10% of all X-rays from a C-arm. So 90% will be through Bremsstrahlung, and 10% will be through characteristic radiation. I've got my poor drawing here of an atom. We've got the nucleus in the middle, and then we've got the various shells with electrons orbiting around the nucleus. So you've got the first shell with the lowest energy, the second shell with a higher energy, the third shell with an even higher energy. And so if you remember from a previous slide, we've got a source of electricity here that heats up the cathode. The cathode causes release of electrons at high speed. Some of these electrons are gonna orbit around the tungsten atoms, decelerate, and then that deceleration is going to cause the release of X-rays. But some of these electrons going at high speeds will have a very high energy, high enough that they can just sort of go at the right time, at the right moment, and hit the inertial electron here. And because they hit it, what happens is they displace that electron off the atom entirely. And so then what happens is you've got an atom here with the first shell that is empty, and you will need that to be filled. So you will get on the right hand side here is that the electron from the higher energy shell will then go to fill the place of the electron that was knocked off, and by filling that place from a high energy to a low energy, it releases energy in the form of a photon or an X-ray. And that is characteristic radiation. Why is it called characteristic radiation? Because essentially, what happens is that the distance from this outer shell to the inner shell is fixed for tungsten and is fixed for any other material. So the amount of energy released is going to be fixed depending on the material that you're using, and that's why it's called characteristic, because based on the energy released, you can identify the material itself. Unlike Bremsstrahlung, where X-rays are basically of various different energies. So now that we know how X-rays are being produced, it is important to have a way of quantifying them and measuring them. And there's really two big ways of doing that. One is through deciding how much X-rays are being produced, and thus how much ionization are we creating, and that's exposure. And the other way is by looking at how much X-rays are being absorbed, and funnily enough, that is called absorbed dose. In clinical practice, we don't tend to use exposure as much. So mostly we focus on how much X-rays are being absorbed rather on how much X-rays are being produced or how much air is being ionized. But for the purpose of the exam, it is useful to know that exposure just means the capacity of X-rays to ionize air particles. And so that reflects how much X-rays are being produced. The more X-rays you have, the more air there is going to be that is going to be ionized. That is measured in two ways. The SI unit is coulomb per kilogram, and the non-SI unit is called Röntgen. And this is again probably more relevant for the MCQ exam. You could be asked about these sort of niche little things. The one that is more relevant in practice is actually the absorbed dose, and so that tells us how much X-rays are being absorbed by the tissue. And the definition on the slide there is sort of radiation delivered per unit of mass. This is measured in a unit called gray, and so the SI unit of that is joules per kilogram. And so if you remember, joules is a measure of energy. So basically, this is how much energy is being delivered per unit of mass. So kilogram is a measure of mass. So a joule per kilogram is a gray in the context of radiation. Because the absorbed dose is the one that is more relevant in clinical practice, we'll focus on it a little bit more. And so the absorbed dose is basically, like we've said, the amount of radiation being absorbed by the tissue. We measure that in gray. But if you remember from the beginning of the talk, we have different forms of ionizing radiation. So we've got X-rays, we've got gamma rays, we've got alpha particles. So while the absorbed dose might be the same, so let's say, for example, it's an zero point 0.2 milligray of absorbed dose, the biological effect might be different depending on whether that zero point 0.2 milligray is of X-rays or is of alpha particles, because zero point 0.2 milligrays of alpha particles will have more of a biological effect than zero point 0.2 milligrays of X-rays. And so we basically calibrate for that by using the equivalent dose. So it accounts for the different biological effects of different ionizing radiation. And it does that by using a weighting factor. Luckily enough, for X-rays, the weighting factor is 1. So if you've got zero point 0.2 milligrays of absorbed dose for X-rays, it will be zero point 0.2 milligrays. Whereas for alpha particles, you will multiply that by something higher. So I think it's, let's say 20. So zero point 0.2 milligrays will be effectively a biological effect of a much, much higher absorbed dose. So that's the equivalent dose. The effective dose is similar, but it accounts, rather than accounting for the type of ionizing radiation itself, it accounts for the type of biological tissue that is absorbing the radiation. And that just reflects the idea that different tissues have different susceptibility to injury by radiation. And so that's also another weighing factor that is multiplied depending on the type of tissue. So if it is a tissue that is quite susceptible to radiation, then that weighing dose will be high. If it is a tissue that doesn't have that high susceptibility, then that weighing factor is going to be low. Both of these are measured in sieverts, and you will see this in practice, usually in the sort of forms of millisieverts rather than sieverts. But that is their unit, and it is an important unit that you need to be aware of. There is one more unit of measurement which is actually very important, and I did get asked about this in my SOE exam. I was asked specifically about the dose area product. And so the dose area product is simply the total amount of radiation that is delivered per procedure, and it is measured in grays meter squared. I apologize, I think this is wrong. So it's not grays per centimeter squared, it is grays centimeter squared or grays meter squared. And basically, it reflects the amount of radiation being absorbed and multiplies that by the area of tissue that the radiation is being delivered to. And you will see this on your images. So if you look into PACS after you've had a procedure done, you will see this image of PACS. I have brought this image from actually one of the procedures, and you can see here the dose area product is 0.005 grays meter squared. There is a little bit of another niche detail. Probably you won't get asked about this in the exam, but it is good for your understanding. These measurements, so whether we're looking at the absorbed dose, the effective dose, or the equivalent dose, or the dose area product, can be calculated or can be measured. So something like the absorbed dose, which is basically the radiation delivered per unit mass, or the biological effect of the tissue in effective dose, isn't something that is measured. That's quite difficult to measure. So it is something that is calculated based on algorithms and data that we have. However, the dose area product is something that is actually measured through the fluoroscopy C-arm. So this value here in this image is something that is actually measured. Okay, so I've got a couple of MCQ questions here. Let's give it a go. The first one is about the units and measurements of ionizing radiation. So please pause the video, have a little think. This is a multiple true-false question, and we'll post the answers in a second. All right. So the answers are here. The first part A, the gray is the SI unit of absorbed dose, which is 1 joule of energy absorbed per kilogram of tissue. That is correct, as I've explained. You've got two things. One is about the amount of X-rays being produced or exposure, and the other is about absorption. So absorption is measured in gray. That is the SI unit. It is joules per kilogram. B, the sievert expresses absorbed dose to tissue without any adjustment for the type of radiation involved. That is false. If you're not adjusting for the type of radiation involved, that is just the absorbed dose, which is in gray. If you're adjusting for the type of radiation involved, then that will be the equivalent dose. And if you're adjusting for the type of tissue, then that's the effective dose, and these are in sieverts. C, the becquerel is a measure of radioactivity defined as 1 nuclear disintegration per second. That is true. The older unit of this is the curie. D, effective dose takes into account the differing radiosensitivity of the various organs and tissues exposed. That is true, as I've explained earlier. If it is equivalent dose, then we're looking at the type of ionizing radiation. But if we're saying effective dose, that is the sensitivity of the tissues. And then E, the Roentgen is the current SI unit used to quantify a patient's ionizing radiation exposure in clinical practice. Now, that would have been true if they said it is the non-SI unit, because the SI unit of the exposure is the coulombs per kilogram. So it's a small little detail. We'll go to the second question. Of the following, the investigation delivering the highest effective radiation dose is? Again, pause the video, have a think, and then we'll answer this. All right, so the correct answer is CT abdo-pelvis. This is again a very common question. It can pop up in the exam in different forms. You can have a comparison between different types of X-rays, and they'll ask you to rank them from least to most. It can come up as a single best answer question. So generally, when you want to think of it, usually CTs will have more effective radiation dose compared to any X-rays. And when you start looking at X-rays, X-rays of the chest will probably be the least amount of radiations. X-rays of the lumbar spine will be the highest amount of radiation, because if you think of the lumbar spine, it has quite big vertebrae. It's got the sacroiliac joint, it's got the pelvis, so there's quite a lot of bone in there. So a very high amount of effective radiation dose. So if you wanna order it from the highest effective radiation dose to the lowest, probably the highest would be the CT abdo-pelvis, followed by the CT head, followed by the isotope bone scan, followed by the epidural injection, followed by the chest X-ray. And if you want to look at X-rays in particular, probably the lumbar spine will always be the most, followed by the thoracic spine, followed by X-rays of the face and the skull, followed by chest X-rays. And that's the end of the session. I hope you liked it. Hopefully, in the next session, we will look a little bit more into why ionizing radiation causes damage to the tissues, the types of damage that could happen, and the regulations in place to try and reduce that amount of damage.